So I, as Jerry mentioned, work for NIST, National Institute of Standards. And I'm just going to start off with some quick disclaimers. Basically, this talk is my talk and nothing in it should be taken to be a recommendation or endorsement by NIST or the government. And then also very important is the fact that all of this work I'm showing is the results of collaborations. So a lot of work was done by other people, and I'm just going to tell you about it. So not really necessary for this particular group, but of course, talking about X-ray spectroscopy, it's important to ask sort of what are X-rays, and we know they're light of a certain energy range. But a different way to look at it is to say that X-rays are in fact probes, right? So what is an X-ray is a question of sort of, we can define it by the measurements that we're actually trying to make with them. And specifically, in my talk, I'm going to be limited to near-edge spectroscopy, which again, is a quick reminder. We could look at the absorption of a material as a function of the energy of the incoming photon. And we see in all materials a general trend like this, whereas the energy gets higher and higher, the absorption goes down. But at certain energies, there are these strong jumps or edges, and these are where there are core level resonances. So when I say near edge spectroscopy, I'm referring to things dealing right with these core levels, right? So now, to me, X-rays are a probe of electronic transitions into or out of these core levels of the atoms. And so immediately this gives us sort of the two hallmarks of X-ray spectroscopy, right? That we say we're element specific because each different element has different energies of its core levels, and also that our probe is localized, which is to say the core orbitals around an atom are localized in space, and so excitations are going to be localized on that atom, at least initially. But the flip side, of course, is that the core levels themselves aren't particularly noteworthy, at least, right? They don't participate in any sort of chemical bonding, right? So the structure of them doesn't change much from system to system. But of course, the core levels are only half of the electronic transition. And so we're really interested in either X-ray absorption, where we're transitioning into unoccupied orbitals, or emission, where one of the occupied valence states is falling down into the core. And these, in fact, do participate in bonding or change dramatically from system to system. And so the hope then is that we can use X-rays to gain some sort of information or understanding about the systems that we're trying to study. And the range of this is quite broad, right? So it can be very general in terms of just trying to understand what elements are present in the system, to much more specific things, trying to understand how the atoms are actually arranged, how the electronic system behaves, and of course, how all of these things change in response to external, applied external things like changing the pressure or changing an applied electronic or magnetic field, and what all the interplay is. So these are all things we hope to understand using X-rays. Of course, when we carry out a measurement, what we get is some raw data, which at least tends to look something fairly simple. If we have a line plot of intensity versus energy, or maybe we have 2D or 3D plots where we're varying one or more things in our experiment. And these plots, this data, it doesn't directly tell us what's happening in the system, right? This isn't the final story. We need to understand what this data means. And so my talk today, I'm going to be trying to make the argument that you can use computational approaches to really help fill out this picture, to help you understand what you're actually measuring in the experiment. And so with that, as by way of introduction, I'm going to talk just slightly more about sort of the challenge of computational spectroscopy, and then also sort of two ways of looking at the interplay or interaction between calculated spectra and measured spectra. So when you carry out an experiment, we're sending in an X-ray and measuring some response in hopes of learning about the material. But what we're actually measuring, in fact, is an excited state. We're not measuring the material itself, we're measuring the material's response to an X-ray probe. And both the electrons and the atoms in the system are going to react and change based off of the fact that we've shown X-rays into the system. And we can have a variety of excitations that are caused by this, whether they're electronic excitations, vibrational excitations, or some interplay between the two. And so the whole conceit of computational spectroscopy is that we can provide a straightforward way to go from a description of the material to a ground state understanding of the material. So we compute what the ground state looks like, various ground state properties. And then on top of that, we can compute the X-ray response. And so we're able to go backwards and forwards between this literal description of what the material is, how the ground state behaves, and how it looks under X-rays. And so this leads directly into what I refer to as the forward problem, which is this idea that if we know the structure of our material, can we accurately generate the X-ray spectra? And you might think to answer this that we would then require some first principles or ab initio theory, right? So that we can make this. But this is probably too strong of a constraint. What we really just need is a sufficiently general theoretical approach. And by this, I mean that it needs to hold for the class of materials you're interested in studying. So that if you're, we'll talk later about studying a battery material, then it's okay to have various dials and convergence and tweaking parameters, as long as you don't need to tweak them based off of the charge state of the system, right? So as long as your theory is still predictive, then it will work out fine. And the answer to this question, though, from structure, can I generate accurate spectra, tends to be yes. So for broad classes of materials, we can do a fairly good job of generating a spectrum that will match what is measured in experiment. But what good is this? Well, what can we learn from this comparison between theory and experiment? And the first thing we can do is simply focus on what doesn't match up correctly. Right, so there's this idea that nothing is so perfect that it can't be complained about. And from here, we can try and learn about the approximations we made in the theory itself. Right, so we're assuming that the experiment was very well done, very well quantified. And so these disagreements are due to problems in our theory or shortcomings. And we can sort of grossly categorize these into two different groups. The first is that things we've included in our theoretical approach, but we've necessarily made approximations to. So what's there is actually wrong in some sense. It's an approximation. And one example of this would be we use density functional theory to describe the electrons in our system. Density functional theory is very popular because it takes all the complicated mini electron diagrams and terms and condenses them down to a simple functional of the density, which we know isn't actually, it's not the correct density functional. That's sort of unknowable. And so there's some approximation here. The other option are sort of terms we've simply completely left out of our theoretical approach. And this could be as simple as often we leave out sort of vibrational or thermal disorder in our system. We almost always in condensed matter leave out the dynamics of the excited state, electron and vibrational coupling terms. And then we also leave out sort of higher order excitation terms as well. But as I mentioned, luckily these tend to be fairly minor. So we tend to be able to make a good comparison between theory and experiment. So the other thing we can focus on is trying to use the calculations themselves to identify the origin of various features in our spectrum. So because we have this direct mapping from the structure all the way to the spectra, if we want to know if a feature in the spectrum is due to a particular structural motif, we can simply change it or modify it and see right away what the effect that has. On the other hand, we can think about this problem sort of in the other way, which is the idea that if we've measured a spectrum or set of spectra, can we generate accurately the structures that must be there in the experiment itself? And this comes with a number of challenges. The first is that, of course, well, not of course, but we would tend to think we need an accurate solution to the forward problem. That if we can't accurately generate spectra from a structure, how could we hope to go the other way? The other challenges are simply that sometimes many structures can lead to similar spectra at the X-ray edge. And of course, the problem as posed is very open-ended. And to attack this, the first thing is to simply use an appropriate theory tool. So to understand the bounds of where the theoretical approach you're using is actually valid and where it will give you good results and good approximations. And to attack the other issues, we don't want to use only the spectrum. You tend to know more about your experiment than just what the X-ray spectra is. Certainly you ought to have an idea of the composition or other materials properties that could help constrain the search. And so with that, I'd like to spend just a few words talking about the theory approach, the Bethe-Salpeter equation, and the ocean code used to carry out these calculations. So to toss up a diagram, we have a photon, X-ray photon coming in as the dark blue squiggly line. It's absorbed by a core level electron, which is excited up into the conduction band and is this forward moving arrow, and leaves behind a core hole, which is the backward moving arrow. And this diagram can be written sort of in the same way, that you have your electron photon operator, D, acting on the many-body condensed matter ground state. And then you have this two-particle Green's function that describes the electron and hole. And so to go about solving this, we need a good enough description of the electron and hole states and a good enough approximation to the excited state. So how the electron and hole interact with each other and with the system itself. And for that, we turn to the Bethe-Salpeter equation. And the Hamiltonian can be written in terms of three terms, the first being the electron term, which for our work, we use density functional theory, or DFT, plus a self-energy correction through the GW approximation to generate the eigenstates of the electrons in our system, of the valence or conduction electrons. And this automatically then builds in all of the information about the system we're in, so the ion positions and so forth. The next piece, of course, is to describe the core hole that's left behind, which is a bit simpler of a term, but importantly includes spin orbit splitting. So if you're talking about an L2-3 edge, then it's important to include the splitting of the 2p3 halves and 2p1 half states. The last term then are the interactions between the electron and the hole, and here we stick to lowest order in the BSE. The first is the so-called direct term, which is an attractive screened Coulomb interaction between the electron and hole, which is responsible then for excitonic binding, and then a repulsive exchange term, which can be minor for K edges, but importantly leads to or contributes to the intensity mixing of the L2, L3 edge for things like transition metals. All of this is packaged together in the ocean code, which is a nice free open source code. You go to this site to learn more. And it's the result of a number of people working over the years, a couple different publications out. As I mentioned, we're building on top of the density functional theory description for our electronic states. And for that, we can interface with two different external codes to get that those calculations. And then for the results I'm showing today, they're almost all were done with quantum espresso, though I do show some GW calculations that were carried out using Ammonium. And then Ocean itself can do a variety of spectroscopies. We can do valence UV, as well as various X-ray spectra, absorption, emission, non-resonant scattering, and also bricks. And so here's a good point for questions.
All right, that's a great start. Thank you. It might be getting a little bit ahead of ourselves, but in the theoretical framework that you've laid out for us, what do you think would be the one biggest piece that's missing? Or is that something you'll come back to later?
I'll point out a couple failures at the end. The biggest piece that's missing is a system-dependent question. So for some systems, the biggest piece that's missing is a good description of the electronic ground state.
Okay.
Though often that can be fixed somewhat with GW or more recently maybe higher further approximations to DFT. In some systems, the biggest problem is a lack of electron-phonon coupling in the excited state. Famously, and I won't show these results because they look terrible, but the nickel L edge of nickel oxide does not match experiment with this approach, which is likely due to the lack of secondary electron-electron excitations. So the BSC approach sort of assumes that the majority of the excitation is the single electron hole, and then the system interacts with it via plasmons primarily. And so if you have a localized DD star or charge transfer excitation that's on site, that's not captured in this approach. And so for nickel oxide, that would be the largest source of error.
All right, thank you. I'll remind everyone to type their questions into the chat as the lecture proceeds, and you should continue, John.
Okay. So now I'm going to jump into going through a couple different examples to sort of talk through some of the things I identified from the sort of the forward or inverse problem of things we can do comparing experiment to theory. And the first is looking at this Spinel lithium titanate system. So this, the reason this is an interesting system to look at is it's thought that maybe it could be useful as a battery anode. In particular, it has two things to recommend it. The first is that as you change lithiation, the volume doesn't change very much. And so hopefully this means that you could minimize strain or cracking or degradation through charge cycles. And the other thing is that it has a favorable potential, so you don't take too much of a hit to your energy density. Unfortunately, it doesn't have great electron conductivity. And so we want to try and understand, can we improve the conductivity? Can we improve the lithium mobility in the system to make it a better battery? And so if you want to improve conductivity, you might think we'll start with trying to dope it. And so this is what the group did. They looked at adding manganese to the system. And we know that when you dope something, you're going to change its structure and its chemical properties. And the first question you might want to try and ask yourself is, where do the dopants actually go in the system? So they can preferentially replace one of the lithium sites in the cell, which are shown here, or conversely, they could replace one of the titanium sites, or, and I haven't shown, they could go in one of the interstitial regions. So it's not particularly obvious from a single static view, but there are some gap spaces that could easily accommodate an extra atom in this cell. And so with these three options, titanium, lithium, or interstitial, we first want to try and cut down the number of options of things to check, right? Because we're trying to go from, we'll end up trying to go from a spectrum back to the structure. And so the first step was to calculate the total energies of various manganese dopant sites. And within each class of dopant site, we can sort them by energy and find the most favorable sites. And that gets us down to these four options, since the titanium 16, D2, and D1 were fairly similar in energy. And so the next step was then to simulate the manganese K edge for these spectra. And so that's what's being shown here. So we have the top curve, the thick black line, is the measured manganese K edge of the manganese doped lithium titanate. And below it in the various colors are simulations at different dopant sites. Sorry. And as we see looking through this, the first three don't really match at all. And it's not until we get down to this thick, bold red line that we see actually very good agreement between the prediction and the theory. So this tells us that the lithium 8A3 site really reproduces well, and that's likely where the manganese is substituting. The downside of this from a battery perspective is that this in fact reduces the lithium mobility in the system. So by sitting on the lithium lattice, the manganese, while it may improve electron conductivity, it drastically reduces the lithium mobility. So that's really too bad. But we were able to see where it was actually sitting by using calculations. The second system I want to look at now is this class of lithium oxides. And so we're continuing in the vein of talking about redox and lithium batteries. And another one of the goals in the battery design is that we want to be able to move reversibly, reproducibly, without damaging the system, every possible electron in and out every battery cycle to really build up the energy density of our system. And as you remove more and more, it can be a question of where are the electrons actually coming from in our system. And in particular, there's this question of, do the oxygens themselves start to lose charge? Most of, in a transition metal oxide system, can you remove enough electrons that the oxygen starts to oxidize or form some sort of peroxide dimers, things like that? And the question then is, how can we actually determine whether or not this is happening? And one way to look at it experimentally might be through bond length changes, using something like X-ray scattering, if the other realities of the system allow it. But this can run into problems as well if your system is highly disordered. You could consider probing it with X-ray absorption spectroscopy, either looking at the oxygen K-edge or looking at the transition metal to try and answer the question through elimination. But there's a problem that X-ray absorption can lead to sometimes misleading or convoluted answers, because while changing the electron density changes the allowed transition, so you can change the intensity at the edge, it also changes the screening behavior of the rest of the electrons in the system, which in turn affects the intensity of the excitation, the strength of the excitonic binding. And so what was done instead was to try and look for a fingerprint of peroxide or oxygen oxidation using RIX, or resonant inelastic X-ray scattering. And I'm just going to briefly walk through a cartoon version of what's going on in RIX. So an initial X-ray is sent into the system. It's absorbed by a core level electron, which is then excited up into the unoccupied states. And this electron and hole will have some interactions, some excitonic effects or things like that, but it'll only live for a few femtoseconds before the core hole decays. One of the decay paths available is that another electron in the system, so from one of the occupied bands, can fall down into the core hole, emitting an X-ray because it needs to conserve energy. And this final state, conduction band electron, valence band hole, also can have some sort of excitonic binding. And it's important to note that the energy of the outgoing X-ray will be determined by the energy of this exciton in the system, right? Because the total energy needs to be conserved. And so this is we're looking at lithium peroxides, and specifically then we're looking at the oxygen K-edge of lithium oxide and lithium peroxide. And so from the dipole selection rules, we know that the final state hole has to be a 2p hole in the valence, and the final state electron also needs to be p-like, because we're talking about transitions in and out of the 1s orbital on the oxygen. Now, for divalent oxygen, we have a closed shell, so the lowest absorption would be into something like a 3p-like state. However, if we've oxidized the oxygen, we no longer have a filled 2p shell. And so conceivably then the lowest absorption state would go into a 2p-like electron system. And so we can make this conjecture that a 2p whole 2p electron is going to be more strongly localized, which in turn will lead to a stronger excitonic binding in this final state between the valence hole and the conduction band electron. Okay, so Rick's experiments and calculations were carried out. And so what I'm showing here with these plots are now what referred to as Rick's maps. So on the y-axis, we have excitation energy. On the x-axis is the measured emission energy. And then the intensity of the signal is shown in the colors. So the blue is not intense or zero background noise. And then as we build up green, yellow, brown, white is getting more and more intense. What we can notice in the lithium oxide is that there's a single emission line, single feature. And this isn't too surprising. If we look at the density of states in the system, we see that in the occupied bands, there's this single large lump of oxygen 2p states. And so this leads to a single emission line. If we go now instead to lithium peroxide, we can first note that there are two emission features now. And this, once again, arises naturally from the density of states. The oxygen 2p occupied states are split into two groups. The other thing we can notice, though, is that as we go towards threshold, so at lower excitation energies, we see a shift in the emission energy, this feature. So this is circled in red and blue in both the measurement and the calculation. So we see a shift to lower emission energies, which is telling us that there's a stronger excitonic binding in the final state for these states. And further, using the code, we can actually plot out what these states look like from the calculation itself. So that's what I'm showing here. On the right is the excited electron density in yellow. And on the left is the excited hole density in blue. And we can see that these are in fact p-type states, strongly localized on the peroxide dimer. And so in fact, this emission energy shift we see in the RICS is a fingerprint of highly localized exciton, and in this system there are oxidized oxygens.
All right. Yang Ha, you had a question?
Yeah, so I just want to have a brief idea, like how expensive are these calculations? Like how long it usually takes to get say, a publishable results? Or do we need like a supercomputing cluster to run these calculations, or can we do it on our own computers?
So that will depend on this unit cell size. But the primary cost in these calculations is in fact the DFT stage. And the reason for that is because we require empty states. So I don't want to be misunderstood on that point. So if you're only doing DFT to get a converged ground state density, you think that DFT is very cheap. But once you start adding a bunch of unoccupied states, because we need transitions into the conduction band, that adds to the calculation. All of the calculations I've done have at most been carried out on, I've done and published, have at most been carried out on a small cluster, a 12 node cluster. But primarily those were in fact broken into smaller pieces. So I wasn't running a single calculation over the entire cluster. I was running multiple calculations over subparts. But all of this filibustering tells you that I don't actually have a good data set. For a very small unit cell like lithium fluoride or diamond, I've run RICS calculations on my laptop on a plane when I got myself locked out of my cluster and needed to fill out the slides for the talk. Not recently. So these are in fact feasible on small computers, I guess.
Okay,
but they're much more expensive than say like a FEF calculation.
Mm-hmm. Okay, so experience-wise, say if I have zero experience in this kind of code, so how easy it is for me to start a calculation, or there are lots of parameters I have to play with?
The dangerous parameters, I think the biggest danger is in the DFT calculation. And DFT is a fairly robust theory, so you can put in a fairly absurd, you can put in a fairly absurd set of atomic coordinates, and it'll run, and then your answer will be pure noise, and there's nothing really to tell you that you've done that. Once you know that that your input structure is correct, and that the parameters for the DFT run are reasonable, the ocean run itself is fairly straightforward because the parameters there are strictly quality parameters, right? So instead of doing integrals, we do sums over grids. And so if you increase the grid size, the sum more closely resembles the integral, your answer converges fairly smoothly.
Cool, thanks.
But there might be people lurking in the chat who can call me a liar on that answer.
Well, first, Karina, you have a question?
Yes, hi, John. So my question was about the RIX picture that you showed. So, and you said that you could use some, yeah, exactly. So we have this, you have the issue of wanting to get some information on the binding, but also on the electronic structure. And I was wondering if the effect of vibronic coupling could be used, assuming, of course, that you have the experimental prerequisites and feasibility, because I see that in the elastic line, again, you have this kind of a feature that might be what we also already talked about. And I was just wondering if that could be that, and if there's, with maybe higher resolution, you could get some more information out of that.
Yeah, so you're asking about in the experiment,
Yeah.
you can see some green along the elastic line
Yeah.
in the measurement.
Yeah.
In the theory, it's strictly dark blue there because ocean doesn't calculate things along the elastic line. These sorts of features, especially because this material has a band gap, and ocean is only calculating the electronic structure and the electronic part of the RIX. So the features along the elastic line are likely are lower energy excitations below the lowest electron hole excitation the system can do, and likely related then to vibrational modes in our system. There's a lot going on in this particular one. You'll see, and I skipped it because it doesn't agree, but higher in energy between 534 and 536. Let's see if I can get my mouse. You see this guy in the experiment. You see this in the theory. So it's likely that we're seeing a bit of degradation already. So that's going to make further comparisons perhaps a bit harder to do. Okay, and then the actual question is whether or not you could try and sorry, I talked on background and then I forgot the precise question.
That's okay. So you were saying in the beginning that getting information on the oxygen oxidation, that there are two possibilities, or three actually. So there's the measuring the bonding lengths, and the second one was to do some absorption spectroscopy and basically the RIX that you did. And I was just wondering if analyzing these structures like in the elastic line could help to maybe kind of like do both.
Yeah, so that's a good point. So the sort of low energy, certainly the elastic line, and then and possibly the tailing you see, low energy in the measurement here, are both, well, certainly the elastic line is due to vibrational coupling, And so the idea is, well, the vibrational modes of O2 should look differently than the vibrational modes of O2 minus should look different than, or not, the modes look the same, the modes are, but the energies will be different as you oxidize the oxygens. And so maybe a high resolution look at the elastic, at the phonon features near the elastic line could actually tell you what energy these vibrations are going at. And that might tell you more about the oxidation state as well. Was that sort of your question?
Yeah, exactly. Yeah.
Yeah, possibly. I don't know.
Hi, John, this is Maria. So I think you're saying that by using explicitly, we can excite the phonons, move the atoms away from the equilibrium position by the amount that we expect from the phonon excitation, and then we do the Rix calculations, and then we should see the effects of the bibonic coupling?
No.
No. Okay. I'm misunderstanding.
Yeah, no, this would be to try and go after actually looking at this, you would need to go beyond.
You would have to actually calculate the cross sections.
Yeah.
Electron phonon cross sections.
Yeah, and there's been some more recent work on this. This is all, electron phonon vibrations are very well known and easy to do in finite systems.
Right.
With countable modes. There has been recent work on trying to do these sort of dynamic Rix in more extended systems. There's been success in aqueous systems, but there I would claim that those are just messy molecules. But I'd have to look up citations to get back to you. But specifically within the ocean code, no, there's no way to access these sort of dynamic vibrational effects.
I see.
I'll talk in the next thing about looking at static effects, so the effects of static disorder in your system.
And I want to use this opportunity. If anyone's interested in computer time, we have available computer time for free for open science research. I put my email in the chat box if anyone's interested. Sorry to steal your time for advertisements.
All right. We have two questions which we'll hold for the end, and you should go ahead and continue, John.
Okay, so the final system I'm going to talk about is ammonium nitrate. Work over a couple different years, and so ammonium nitrate is a nice simple system. You can think of it as sort of it's an ionic crystal, except for the ions are complex, they're multi-atom ions. And it should be very easy for us to calculate. There are no D or F electrons, there's no magnetic ordering, none of the things that might complicate our lives. So the first thing we did when trying to look at the system is I thought this will be very simple, and I ran X-ray absorption calculations at the nitrogen K edge. And I got the results that are shown here. So on the bottom is the experiment in the solid blue, and then above it, we've displaced above it, are two different plots of the calculation, and the only difference is we've increased the broadening. Sort of an artificial broadening was added to these calculations. And what's fairly clear is that the calculated spectra don't match the experiment whatsoever. There's this strong peak. There's this strong peak here in the calculation that even turning up the broadening to a frankly ridiculous amount doesn't get rid of. And so we need to try and understand, well, what went wrong? And the first assumption might be that, well, we just put in the wrong structure. That happens sometimes. Or we might call up our experimental collaborators and tell them they measured the wrong structure. But in fact, neither of those things happened. What's actually going on is that for these types of calculations, we tend to use what you could call the crystallographic coordinates. So I've drawn atoms in this square lattice, and you see all the atoms are nicely arrayed in perfect order. But this isn't what happens in reality. In reality, the atoms are always moving around. They're always vibrating. with both thermal and 0-point motion, and it's only on average that they're centered on these positions. And this has been known for a while that it can, and I only put in one example, but there are others in the literature, that this can lead to new features, and something you need to account for. And then the question is, how do we account for it? How do we properly simulate these types of systems? And one popular option is that we, instead of using the unit cell, we build a larger cell so that we can start to disorder the atoms. And then the question, oh goodness. And then we can use, and then the question is, how do we generate these larger disordered cells? One popular method is that we can simply use what's called ab initio molecular dynamics, where we treat the nuclei as classical point particles that are allowed to move around along the potential energy surface of the electronic system. Then you couple the system to appropriate thermostats, set it at the right temperature, and let it go, and it builds you an ensemble, a set of structures you can use to do this kind of averaging. But this, in fact, won't work well for our particular system of the ammonium nitrate. And to see that, we can look at the vibrational density of states. So these are what vibrations are there in our system as a function of wave number here. And we see that there are actually a lot of very high frequency vibrations in our system because our system involves these small molecules, the NH4 and the NO3. And in fact, if we are only moving things using ab initio molecular dynamics, we're only exciting modes sort of up to the thermally accessible ones, which are down here, KT. And so instead, we built up a way to properly sample all the different vibrational modes of our system. And to take a step back for a second, that's because we know these phonon vibrations are quantum harmonic oscillators. So even at 0 temperature, they should have this half quantum of 0-point motion. So they shouldn't be completely, vibrations shouldn't be completely absent. And so to see the effect this has on the spectrum, we can walk through it. So here I'm reproducing the initial plot I showed. So now in pink at the top is the calculation using the fixed atoms in their relaxed positions. If we do a sort of semi-classical approach, using only the thermal occupation of the phonons, we end up with the green curve here. And then if we finally do sort of a full quantum calculation, which has both the 0-point and thermal occupation, we end up with the red curve here. So we see a dramatic change as we go from pink to green to red. And in particular, I want you to look at this peak that's been labeled, which is resulting from the ammonium atoms, or from the ammonium nitrogens. And as we turn up the disorder, as we include thermal and then full quantum phonon occupations, we see that this peak seems to completely melt away. But what's actually happening is it's getting broader and broader and broader, and it's actually leaking out here below the nitrate. So this lowest part of the shoulder in our measured spectra is actually due to the ammonium. It's just so broadened by the disorder of the hydrogens that it takes up this amount of space. And so having finally fixed the problem of matching the X-ray absorption, we can try and hope to look at what the RIC spectra looks like and compare that between theory and experiment. So here again, this is just the X-ray absorption with arrows pointing to specific energies. And these are the energies that we're taking the RICs at. And the comparison is now shown here. So the thicker blue curve is showing the experiment. The overlaid on it in red is the ocean calculation for each of these energies, and one additional high energy one to sort of show the non-resonant emission. And the first thing to notice is that we do a fairly good job of calculating the large scale changes as we change in energy, right? So there's shifts in how the emission looks, and the ocean calculation follows that okay. But the thing that might be distracting you from that agreement is what's going on down here. And specifically, this is a peak in the calculation that we can say is coming from the nitrate sigma bonds, which is showing up very clearly in the calculation, and perhaps not so much in the actual measurement themselves. And so what's going on? So here we are looking at the non-resonant emission, and maybe you'd believe me if I told you there was an experimental peak at the nitrate sigma bonds, maybe you wouldn't. If we go down in energy of our initial excitation down towards threshold, we can actually see that this peak is in fact there. So in the experiment, we see a sharpening, and in fact a feature that is aligned in energy with the predicted one in our calculation. But it seems like it's much too weak. So we want to try and understand what's actually happening. So as I said in the brief section on how ocean goes together is we're generating our electronic states, our valence and conduction band states using density functional theory. But we have the option of trying to go beyond simple DFT and adding in what are called GW corrections. These tend to be very popular if you're interested in the exact energy alignment or band gaps. So if you're, or band alignment for water splitting or what else you might need it for. But GW also can give you, the GW correction itself is actually a complex energy correction. When the imaginary part of that is then related to the inverse lifetime of that state. And for this, we need to remember that what I call the final state in our calculation isn't the ground state of the system. And we know this, we know that there's a core hole with a core hole broadening in terms of absorption, but actually the valence and conduction electrons can also scatter and decay, have their own lifetimes. And what the GW, and this can be from electron-electron interactions or electron-phonon interactions as well. And what the GW method can do is it gives you an estimate of the electron-electron contribution to the valence or conduction lifetimes. So to see how that looks, we did GW calculations on ammonium nitrate, and now I'm showing the imaginary component of the GW corrections as a function of the band energy with respect to the Fermi level. So these are only, all these band energies are negative, right? We're only looking at the occupied states. And we see by and large, the occupied states show very small lifetime broadening. Everyone's clustered down here at 0, with the exception of these states up here, which are in fact the nitrate sigma bonds. So now what we do is we roll in the result, the contributions, the GW corrections into our calculation itself and see how that changes things. And we can see now in red are the ocean calculations using GW corrections versus the green dash were the ocean calculations just using DFT through the local density approximation. And we can see now that there is a large scale difference down here at the nitrate sigma bonds. And there's a significantly improved agreement between the experiment and theory when we account for this relatively short valence lifetime. I forgot to mention it a couple slides ago, but the calculated valence lifetime of these, or valence lifetime broadening of these states was up near 1 EV. And for comparison, the nitrogen 1s, so the core hole lifetime broadening in this system, is only 0.1 EV. So these nitrate sigma bond states are actually quite short-lived. So just as a brief summary, we looked at how we can go from a spectrum to trying to identify the correct structure in the lithium titanate, how we could sort of examine physically what a feature is actually showing us in the lithium oxide systems, and then how we can try and critique the underlying assumptions that have gone into our calculation using ammonium nitrate. So for all of these, you can use the ocean code to sort of help us understand better what's actually going on in our systems. And I just want to mention that NIST has a centrally funded postdoc program with fall and spring deadlines. And if you want more information, you can email me. And with that, I want to stop the talk, and I'm happy to take more questions.
Thank you, John. That was terrific. First question is from Thomas Rossi.
Sorry. Hi, John. Thank you very much for this very nice talk. Actually, this is a perfect timing for me because I started started doing calculations with ocean like a week ago. And my system of interest is zinc oxide at the zinc edge. And I have a couple of practical questions regarding the calculations. So the first thing is I noticed that ocean is not reading the universal UPF pseudopotential format at the moment. I think it's reading only FHI and another pseudopotential format. Is there a plan to be able to read UPF format at some point?
Not by me. So the FHI were convenient at the time, and then much more recently, I've added support for the optimized norm conserving Vanderbilt format, which is a few years back paper by Hammond on that. And with that, with the support for the ONCV comes the fact that two different groups maintain periodic tables that they're trying to test and better pseudopotentials for. So there's Pseudo Dojo, and there's another one whose name is not at the tip of my tongue.
Okay.
And what we're going to do in an upcoming release, because at least Pseudo Dojo has a share alike license, will actually just include those pseudopotential libraries with the code itself to make that quite a bit easier.
Yeah, that would be nice. I spend a lot of time trying to convert pseudopotentials because I did everything with Quantum Espresso for the DFT part, and I was actually trying to improve the agreement of one feature in my spectrum using the Bethe-Salpeter. And yeah, I had some problems converting pseudopotentials and trying to find the right ones. So, okay, that's fine then. And then I have another question related to, so if I get an error message that I cannot troubleshoot, so I cannot identify where it comes from, is there either a discussion forum where we can address this, or do we need to contact you directly?
There's not a discussion forum at the moment.
Okay.
So you can email me. Yeah, I'll leave it at that.
Okay, thank you.
All right, Fer Davila, you had a question?
Yes, just this question is going to sound a little bit mean, John, considering that you probably have the best method out there for calculating this kind of things. I mean, ocean is the best in this sense. But one thing that always bothers me, you know, I come from a quantum chemistry background. One thing that always bothers me with this type of methods is the fact that there is no way of systematically improving the method itself by adding more diagrams or something like that. So I wanted to know what your thoughts are. Is there anything you can think of that would allow you to do a systematic improvement of the results? I know that you are basically trying to fill in the holes here with like electron phonon couplings and that kind of stuff, but I'm talking about the electronic structure, like the self-energy that you're using and the diagrams that go into the electron hole coupling and that kind of stuff.
Well, so I guess there is a straightforward way of adding more diagrams in that you could code in more diagrams. The question is whether or not you could code in diagrams in a way that would make any sense, right? Because you can just start drawing diagrams that include more interaction lines. Ask which ones you,
and that is essentially the question for me. I mean,
yeah.
With quantum chemistry, you know that if you add more, you usually improve. And if you add more and you go wrong, and then you add more, you go right. But with this, you can start throwing diagrams around, and things might really not improve that much. So it's basically, it's like you said at the very beginning, where you have to find the method that works for the type of systems that you have, and then just try to stick to that. Is that basically the bottom line?
At the moment, so there is, the work by Yufeng Liang to try, not with the BSC in particular. He was using delta SCF method,
Yeah.
to try and add in higher order excitation terms in a way that looks a tiny bit like a quantum chemistry method if you don't look too closely.
Yes.
Well, it has this idea of singles and doubles and triples. They just mean something completely different. The other option, I guess, would be trying to use the BSC as a filter to better parameterize your local approach. So I didn't cover any of my competitors, and I really should have added a slide. So there are other BSC codes out there for core level spectra. I'll just say this now. There's the exciting code, and then there's also a Veen2K BSC for core level, and I hope I'm not leaving anyone out. But another method is to do this sort of localized exact diagonalization where you pick a set of orbitals that you're going to include in your problem. So for a transition metal, you include the 3D electrons on the transition metal, you include the 2p electrons on the oxygen atoms that are next to it, and your basis set is small enough that you can think about diagonalizing this.
So this is basically like the multi-reference methods in quantum chemistry, where you basically do an improvement of your basic wave function, and then you add all the correlation you can on top. It sounds like that.
So I'm saying it's possible that you could use BSC to help you pick good parameterizations for a higher order method.
Yeah. And I'm gonna mute myself because John is adding questions too.
Is that John Rare had a question?
It was a comment on these high order terms. I mean, what I'm thinking of is a convolution with a spectral function that you could make from GW hole and particle self energies. So that will effectively add some higher order diagrams.
Yes, I think the applicability is also going to be system dependent.
I mean, so GW contains all the one loop diagram to all orders, right? One particle reducible ones. And then you're talking about adding vertices. Is that what you're saying? But we learned from GW, I mean, that it's not always more accurate if you add the vertices, right? Like, at least at the band gap level, that was not the case.
The GW only refers to the electron line or the hole line, and not both. You need a particle hole Green's function. It's not the same as GW.
I see.